Hi class, we are now on the last section of chapter 16. This is Le Chatelier's principle. We're going to look at what happens to an equilibrium system when a disturbance or a stressor happens, affects it. So Le Chatelier's principle, this helps us understanding if we change the conditions on the equilibrium reaction, what happens to that reaction? How does it adjust in order to fix itself? Because the equilibrium constant stays constant, so it's going to always try to fix itself. There are conditions where the equilibrium constant will change, but the first ones that we're going to look here, it doesn't change. So it's going to have to affect, somehow something's got to change in it to get it back to that where the equilibrium constant does not change. So we call this a stress or stressor, and it's applied on either the reaction side or the product side, and we're going to see what happens with that. So a stress is a change of conditions on the system, change in concentration, pressure, volume of one of the more reactants or products, and the system, the reaction's temperature. So all of these are stressors that we're going to look at here. Okay, so what if we add a reactant? So initially it increases the rate of the forward reaction, but doesn't have an initial effect on the rate of the reverse because everything's going in the forward reaction. The reaction will proceed to the right until equilibrium is restored. So think of it this way. If you're adding a reactant, you now have too much of the reactants. So because of that, it's going to push itself towards producing more product to balance this out. So a good thing is a kind of for every action there's an equal and opposite reaction. So it's not going to just, this amount of reactant's not going to sit there. It's going to force the reaction to go forward. And once it gets in equilibrium again, we'll have more concentration, but it's still in the same equilibrium constant. So at new equilibrium position, there are more of the products than before, and less of the non-added reactants than before, and less of the added reactants than before. So the concentrations are going to change. However, the equilibrium constant is now back and it's restored. So the concentration of reactants and products will be such that the value of the equilibrium stays constant. So the overall here, that the changes that happen will happen to get that equilibrium constant back to what it was. So removing a reactant. So initially, if we decrease the rate of the forward reaction, it has no effect on the rate of the reverse reaction. So the reaction is going faster in reverse. The reaction proceeds to the left until the equilibrium is restored. So in this case, what happens is that we have, say, two reactants, and I'm going to cover this with examples. You pull one of the reactants out, the equilibrium constant is not going to change. So it's going to adjust itself by pushing the products back into reactants. So that's going to cover the reactions that were taken out, the reactant that was taken out. At the new equilibrium position, there's less of the products because the products are now reactants, more of the non-removed reactants have been before, and more of the removed reactant. So it's filled in that gap that was taken away. So at the new equilibrium position, the concentration of reactants and products will be such that the value of the equilibrium constant is the same. And that's the recurring theme here. The equilibrium constant does not change even if you remove a reactant or add a reactant, remove a product or add a product. It's always going to be the same. The initial amounts and what's happened after the change will be different, but the equilibrium will be the same. So adding a reactant will decrease the amounts of the other reactants because it will force into products. So whatever it is going to combine with will also decrease. And it increases the amounts of products because, of course, these reactants reacting with each other, that has to go somewhere. But the K is still the same. Removing a product will increase the amounts of the other products and decrease the amounts of the reactants. Why? Because you're removing something again. So when you're removing it, the equilibrium's going to, that's a stressor, it's going to cover that part that's been removed. So it's going to push the reactants towards more product. In doing that, it's going to create whatever other products have to be produced to cover the one that was removed. The equilibrium shifts away from the side with added chemicals or toward the side with removed chemicals. So this is that where I said for every action there's an equal and opposite reaction. If you take something away, it's going to recover. It's going to push it from the other side. If you add something, it's going to push it to the other side. So whatever's happening, it's going to affect the other side somehow. So adding more of a solid or liquid, though, does not change its concentration, because remember, we do not add those or consider them in the equilibrium constant. Okay, so here's an example, a visual. Here we have N2O4 and we have NO2. Now, when you add more NO2, so first we need to figure, is NO2 a reactant or is it a product? We see it's a product. So if we add more here, it's going to adjust on this side. How is it going to adjust? Well, if we added more here, it's going to push it over here. So we will have more reactant than product. So the equilibrium is going to shift to the left. So the amounts are going to be different once you can see the changes in the concentrations, but the equilibrium will still be constant. So because something was done, a stressor was done on this side, it's going to react by producing more on this side. Then eventually, so you see the system shifts to the left. All right, so the next one, this is a perfect example of what I'm talking about. Let's see. Yeah, so the NO2, when more NO2 is added, it's going to combine to make more of the reactant. Okay, so look at this. This is a good graph once you understand what you're looking at. So here's the original Q equals K equilibrium. This is NO2, this is N2O4. So these are the concentrations. If we increase the concentration of NO2, it's eventually going to decrease, and then it will steady itself out. Why? It'll go back to Q equals K. In order to do that, the N2O4 has to increase. Now you see this is more drastic because it has a 2 coefficient where this has a 1. So that's why you don't see this one as severe of a increase there. But you can see that the same thing, that this has to react. It's got to take what is being decreased. So this is going to increase, and Q is equal to K here as well. So the amounts, the concentrations you started out with are lower than what you end up with after the stressor, but the K is still conserved. All right, so let's take a look at this one. So if we do the opposite, where we add the N2O4, you see where it's increased. So it's increased substantially, but eventually it'll still get back to Q equals K, because the amount it will produce of the opposite. So I think this is, if I remember right, yeah, this is reactant. So it will produce more product, and that's what you see here. Is it's going to produce more product, and Q is established, but not at the same concentrations that they were before. Okay, so if you add more A, then Q is less than K. Why is it less than K? Because we're talking about what happens, the action that happens. So when A is added, remember, if you have more of A, then that means that Q is greater than B. But if you have less A, then you have B, its Q is less than K. So we add more A, but it's going to proceed to the right. It's going to work to get itself back into equilibrium with K. So then it's got to go less than K. I hope I'm making sense of this. Don't think about it as instant, but what eventually is going to happen. It's going to be less, because if you add more A, the reactants are going to react and produce more product. That is why K will be larger than Q, because it will be at a different value once this goes back into equilibrium. So while it's doing that, so let's look at this part here. That's what we're looking at. The action has already happened. So if you add more, it's already starting to adjust, and you will see that's what this means. It's not when we instantly add more A, we're looking at the eventual action of what's happening. And the eventual action is add more A, it's going to produce more product. So that means that K will have more equilibrium. There will be more product than there will be of reactant. And if we add more B, eventually what's going to happen is that there will be more Q. Why? Because there will be more reactant than product, because it's going to push this equilibrium towards the products, which is left. Reactants, which is left. If we remove more A, then Q is less than K. That's because Q is greater than K, because again, it's pushing itself towards A to produce more reactants to cover the amount that was taken. And if you remove B, then Q is less than K because of the fact that A is going to push itself into B to creating more products. In all cases, the reaction shifts to restore an equilibrium position with concentrations or pressures equal to K. So it's adjusting itself to make sure that K does not change. All right, so this is just a little chart. I know what I said is confusing. It will take a little while to make sense of what it is. So hopefully this chart helps you understand that. Okay, so let's do a problem. Determine the direction in which this reaction shifts after the following changes are made. So this is after the following changes are made. It's not an instant once the change has happened. So A, increasing the concentration of H2S, increasing the concentration of H2, or removing S2 from the system. So I'm just going to jump to the answers just to make it easier to understand. So we are increasing the concentration of, this is a reactant. So if you increase the concentration of this, then what's got to happen? It's going to increase the concentration of the products, and this is eventually going to decrease. So that is where Q is less than K. You're going to have more than this and less than this, even though this is what was added originally. Increasing the concentration of H2 is the complete opposite. You have more of this, but to get an equilibrium, it's got to push it this way. So Q will have more than K. Q will be larger than K, and this reaction is going to proceed to the left. You will have less products and more reactant. Removing S2 from the system. So S2 is a product. So what's going to happen? It's going to push it this way. So as you keep taking S2 out, more of the reactant's going to produce that S2. So Q is going to be less than K, and the reaction is going to proceed to the right. Okay, so what about volume? Now we're going to look at gases. Gases, what if we, in a controlled container, what happens in this? So if you decrease the container volume for, and I have pictures of this, decreasing the container volume for a gaseous reaction will increase the total pressure. This has to do with Boyle's law. If you guys remember Boyle's law, P1 equals V1 equals P2 V2. And that is, when you solve for one variable, then you can figure out the other. If you have three variables, you can solve for the one. But what is important here, when you start moving this around, this is an inverse relationship. So if the pressure goes up, then the volume has to go down. And if the volume goes up, then the pressure has to go down. So whatever happens to one is the opposite for the other. So the total pressure increases, then the partial pressures of all the gases will increase. This has to do with Dalton's law of partial pressures. We're just going to focus right now on looking at the gases and the changes. So because the total pressure increases, the position of equilibrium will shift to decrease the pressure by removing gas molecules. How does it do that? Well, we start looking at the moles of the reaction, and that's going to tell us which side has more moles and which has less. And depending on what the conditions are, that's how we're going to see the equilibrium shift. So it's going to shift toward side with fewer gas molecules. So if we decrease the volume, that increases the pressure, then this is going to go for the side, the chemical reaction, which has less, fewer gas molecules. And I'll show you a bounce reaction of this. So if we have 2 moles on the reactant side and 1 mole on the product side, this is going to favor the product side because there's 1 mole. At the equilibrium position, the partial pressures of gaseous reactants and products will be such that the value of the equilibrium constant is the same. I couldn't say it. So it's the same thing, even though we weren't covering it. Equilibrium constant is the same. Okay, so decreasing the volume causes a reaction to shift in the direction that has fewer moles of gas particles. Increasing the volume now decreases the pressure, which means there's more room, more leg room. Spread your legs out. That's going to it's going to favor the reaction that has the greater number of moles. So more moles of whatever side is going to be produced. If a reaction has equal number of moles on both sides, so let's say you have 1 mole of reactant and 1 mole of product, nothing happens. There's no change. It's because it's balanced. So if a reaction has equal number of moles or gas on both sides of the chemical equilibrium equation, I'm getting all these words, then a change in volume produces no effect because it can't go on either side. It's a balanced coefficient. Adding an inert gas. So if you add an inert gas to the mixture at a fixed volume, nothing happens. It's the same as dealing with a solid or a pure liquid. It's not going to affect anything. Changing volume for an aqueous system has no effect on the equilibrium. Okay, so here's a picture. I can show you what happens. So this would be, if you want to, you can look at this different ways. This is increasing the volume, decreases the pressure. So in this case, it's going to look, we have 1 mole and 1 mole. So the total here is 2 moles, and we have 1 mole of product. Because this has more leg room, it can expand. So the gas is going to favor the side that has more moles because it can produce more. So in this case, it's going to be the reactants. On this side, so this looks like it's the change. B is the change. I got this from another book. It's going to, decrease the volume. So when it decreases the volume, it is now increasing the pressure. So there's not as much room, so the opposite effect is going to happen. It is going to go towards the side of the reaction that has fewer molecules. In this case, it's the products. So it's going to favor the products because there's less of them while the pressure is high. So adding a gaseous reactant increases partial pressure, causing the equilibrium to shift to the right. Increasing its partial pressure increases its concentration. Remember, we can substitute these in. N over V, that's, in this case, it moles over volume. It does not increase the partial pressure of the other gases in the mixture. I'm not going to really focus too much on this. I'm just looking more at the changes overall. Adding an inert gas to the mixture has no effect on the position or equilibrium. It does not affect the partial pressures of the gases in the reaction. I'm saying too many words the same. Okay, let's look at this. The effect of volume changes on equilibrium. When the pressure is increased, as it is in this first picture, then this is where it's going to favor moles of gas that are less in the reaction. So in this case, we have 2 moles of gas. This reaction is going to be favored on the product side because there's less of them. Now, if we decrease the volume, the pressure, let me start that again. When we decrease the volume, that decreases the pressure. So now we have more room for whichever one has more molecules to be produced. In this case, we have 4 moles, so it's going to go towards the reactants. It's going to produce more reactants because there's more leg room, it can spread out and so forth. So again, here's a chart to allow you to see the changes that are happening. Which side will end up with looking at more moles or less moles and the decrease and increase. I think I copied that over on this page. So a summary of the changes in pressure and volume. A decrease in volume results in an increase in pressure. That shifts the equilibrium towards the side that has fewer moles of gas. And an increase in volume results in a decrease in pressure, and that shifts the equilibrium towards the side of the reaction that has more moles of gas. A change in volume has no effect on the reaction in which the same number, so if same number, 1 mole and products and 1 mole of reactants, nothing happens. And if the addition of inert gas to a reaction at equilibrium does nothing. It will not shift to equilibrium provided that the volume does not change. Changes in pressure and volume do not affect the value of K. So even these changes, the equilibrium constant is conserved. All right, so let's look at this. Determine the direction in which the equilibrium position of this reaction occurring in a sealed container with a variable volume. So that just means it changes. Shifts after the changes below. So when we look at this reaction, the volume of the container is decreased. So if it's decreased, it increases pressure. So let's just jump and skip right over. This picture does not match, but this is a picture I talked about earlier. So it's just to give you a visual of what's happening. So in this case, if it decreases, the pressure increases, which means not as much leg room, kind of stuck in a very small area. So fewer, it's going to side with the reactant or product that has fewer moles. In this case, we have 4 moles of reactants and we have 2 moles of product. So this is going to shift to the right. In this one, the volume of the container is increased. When it increases, this is Boyle's law, it's going to decrease the pressure because more leg room, you can spread your legs out, you have more room to move, and so you have more room to move. It's going to favor the side that has more moles. And in this case, it's going to shift to the left because there are 4 moles, it's going to favor that side. Okay, so gaseous helium is added to the container while the volume is held constant. Helium is an inert gas. It has no effect. It's not going to affect this whatsoever. And so there is no change in equilibrium, even though the moles up here are different. Okay, so now let's cover the temperature. Last one. Exothermic reactions release energy, and endothermic reactions absorb energy. Hopefully you remember all of this from Chem 111 in that fun thermochemistry chapter. Writing heat as a part of the reaction helps us use Le Chatelier's principle to predict the effect of temperature changes, even though heat is not matter and is not written in a proper equation. So what this means is that if you kind of change the way you look at heat and see it as a compound, it makes it easier to understand what is happening. If you look at heat as not something that you can see or something physical in a sense, you have a harder time understanding this. So change your thinking a little bit and see it more as a compound, an actual reactant or product, and it's easier to understand the changes here. Unlike changes in molarity, volume, or pressure, changes in temperature do affect the value of the equilibrium. So it will affect this and change it. So we are going to look at that. For endothermic reactions, equilibrium constant and temperature are directly related. And exothermic reactions, the equilibrium constant and temperature are inversely related. Okay, so let's take a look at some situations. So if we add heat, so what I'm saying is see this as another compound. You see this as N2, you see this as H2. You know that these are actual substances. Look at this as a compound, a substance, and not as something that you can't see. When you do that, it really helps understand what's happening. Adding heat to an exothermic reaction will decrease the concentrations of products and increase the concentrations of reactants. Adding heat to an exothermic reaction will decrease the value of K. So in this case, if we look at this reaction here, how would decreasing the temperature affect the system? So think of this as an actual substance. If we remove this out, it's just like the other ones. These are going to produce more to recover the heat that's been removed. It's going to shift to the right and have a larger K. Why? Because you're going to have more products and reactants to recover what was taken out. All right, so for an endothermic reaction, heat is a reactant. Increasing the temperature is like adding heat. So if we add heat, again, think of this as a substance and not something that you can't see. If you add a substance of heat, it's going to push towards the products because it's got to adjust for that extra amount that's been added. So it's going to produce more products, and the reaction is going to shift right, a larger K. So adding heat to an exothermic reaction will decrease the concentration of reactants and increase the concentration of products. Adding heat to an exothermic reaction will increase the value of K. And again, here's just a little chart. It allows you to understand what's happening and and what's happening with the reaction shift. Okay, so for an exothermic reaction, heat is a product. Again, look at this like as a substance, and it makes it easier. Increasing the temperature is like adding heat. So when you hear of increase in temperature, think of heat as a substance and, oh, I'm adding more heat. According to Le Chatelier's principle, the equilibrium will shift away from the added heat. That is because it's going to adjust this way and produce more reactants. So the reaction shifts left and a smaller K. Remember, the bigger the K, that means that the equilibrium is more towards the products, and the smaller K means it's more towards the reactants. Nope, I jumped ahead too far. So let's take a look at this here. So we have N2O4, a gas that's colorless, and we have NO2, which I think this is a product of smog, which makes smog look brown. And this is brown. This is brown. This is products. And then we have heat. So if we see heat as a product here, this is an endothermic reaction, right? It needs heat going this way. So the heat is going into, it would be a positive H, delta H, or if it's exo, it's negative delta H. Okay, so let's see what's happening here. A lower temperature, so it needs heat in order for this reaction to occur. It's not going to emit heat. So we have N2O4 and it in this one here. The reaction, if you can look at it, looks like it's really small. It looks like it's negative 75.0, and that's going to favor an endothermic reaction. So this is why you see the gas as colorless, because it needs the heat in order for this to this reaction to occur. So it's going to take the heat and that's why you see the colorless. I know I'm repeating myself. And then on this side, the heat has increased. So because the temperature has increased, you see that the brown, it is now brown. So the high temperature favors the NO2. If it goes into an endothermic reaction, it's going to go into the colorless gas. And if you increase the temperature and force it this way, that's where you start seeing the brown. You see the brown color. This is kind of good because even just color-wise, if you understand that this is an exothermic reaction, so the heat will be pulled away so this reaction can occur, you see why it's colorless. But higher temperature, NO2 is favored, it's brown. The effect of temperature on an endothermic reaction. This is a reaction that you can see when it is with reactants, it's this color. But when it is towards the products, it's this color. So this is kind of cool that you can actually see by color what is happening. If the color is this purple, then this is actually being pushed this way. And if it's being pushed this way, you can see the color of, magenta, violet? I don't know. Okay, the decomposition of ammonia and N2 into N2 and H2 is endothermic. So how is K for this reaction affected by an increase in the temperature? Determine the direction in which the system shifts after the change in K. Identify how the partial pressure of each gas is affected by the reaction shift. So let's just jump ahead and here. So for endothermic reactions, remember K, equilibrium, remember going back to equilibrium constants just in general. The larger the K, more than 1, that means that it produces more product than reactant. A smaller K, less than 1, produces more reactant than products. So for an endothermic reactions, K is directly related to temperature, so K increases. Determine the direction in which the system shifts after the change in K. So if we look at determine, excuse me, I'm getting tongue-tied here. Okay, so let me explain again. K is directly related to T. So if there's an increase in temperature for an endothermic reaction, then that means that K has to become larger. K is going to increase. Why is K going to increase? Because it's going in the opposite direction. If this is an endothermic reaction, the heat is on this side. But if the temperature increases, it means it's being pushed this side. And that is going to increase the K because it's going, remember, K is directly related to T for endothermic reactions. So don't even try to think past that. Just make it simple. Endothermic reactions, K is directly related to T. So that means that if the temperature increases, then the K is also going to increase. It's pushing it towards the products. So determine the direction in which the system shifts after the change in K. So Q is now less than K because it's shifted in this direction. So the system shifts to the right. Identify how the partial pressure of each gas is affected by the reaction shift. So if we look at this, the partial pressure of ammonia decreases while the partial pressure of nitrogen and hydrogen increase. Because it's being shifted to the right, that's got to increase, this has to decrease. And that's it.